Sorry everyone. Let's see if we'll get to this point or not. But this is one of my favorite parts. All right.
Okay, so for today's quick seminar, we were very pleased to have Anurag Anshu from Premier Institute. He's going to talk about quantum decoupling via efficient classical operations and entanglement promotional quantum.
Hi everyone. Thanks to Card for organizing this whole thing. It's very nice to be here, in fact. So I'll talk about this particular work. I don't think I need the mic here, right? Because
I think it's for the recording.
oh, I see. Okay. So should I switch it on somehow? It's on. All right. Great. All right. So this is a joint work with Rahul, who is in Singapore, and it was done while I was a PhD student at Singapore as well. This is going to be a little bit of Shannon theory or information theory kind of talk. But the nice thing about what I'll talk about here is that it borrows ideas from complexity theory or computer science, which was also new to me in some sense. And so I guess I'll pitch these things and let's see how do you guys like it. What I'll do is that I'll kind of take things easy here. I know not everyone here has studied convex-split theory. All of us are from different backgrounds and all. So interrupt me anytime you want. We'll go slowly and we'll try to digest the settings that we are interested in. So first I'll do is that I'll discuss some classical tasks which are relevant for this whole thing. I'll then talk about the quantum version of these tasks. And then I'll go to the results. So this is the task which I'm sure everyone knows about. It's pretty well known and it's been around for around 60 years now, 70 years. So it's the Shannon's result which says that, which asks the following problem. There is a random variable which takes value x with probability p of x. Alice receives many samples from this random variable, n of them. She has to send some communication to Bob in a manner that Bob should be able to output the sequence that Alice received with small error. So this was one of the many results established by Shannon in 1948. This is one of the simplest probably, but also it's very important from information theoretic perspective. The reason why he considered this task is because compression is very natural for any communication, simply because most random variables we want to communicate, they have some bias in their distribution, and there is a scope to send less bits and achieve the task. So what Shannon showed, we all know that the number of bits communicated divided by n, which is also called the rate of communication, is roughly the entropy, which is this quantity over here. And his protocol showed that the error can be made as small as possible. In fact, he also proved that this is the best you can do. And then the idea was, well, you only communicate something known as typical sequences. It won't be important to us, but I just thought to mention out here. Shannon's entropy also captures the information that is there in the random variable, x. So if it is 0, then nothing has to be sent. It's a deterministic random variable. So let me make this task a little bit more complicated. I hope you guys might be familiar with this problem, but I'll do a few simplifications in this picture. First of all, I'll get rid of these n independent random variables. I'll just take one random variable, like one sample from the random variable. And this is for two reasons. First, it kind of simplifies the discussion. It also, gives all the ideas of the task. And the second thing is that it's also very practically relevant. Most scenarios you don't get n independent samples. So it makes sense to just study one sample and how do you compress that. So this is the task considered by Slepian and Wolf. In this case, there's a joint random variable xy. Alice receives an x, and Bob receives a y from the source. The task is that Alice should send some message to Bob in a way that Bob can output x with very high probability that Alice received. So Bob has some knowledge about what Alice might have got. Alice doesn't know y, by the way. And then their job is to do this thing with as low error as possible. So this was considered by Slepian and Wolf in 1973, and it was one of the, in fact, they considered a more general task, which started the field of distributed Shannon theory, which basically where multiple parties communicate to each other and so on. And this is a special case of what we did, but it's good enough for our purpose. So what this showed is that if I looked at the asymptotic and IID version in which the parties receive many independent copies, like x1, x2, xn, and yn, y2, yn. In this case, the rate of communication is the conditional entropy, h of x given y. What's interesting about this result is that Alice doesn't really know y. Even then, you can achieve the same communication as you'd achieve if Alice knew y. That is, if Alice knew y, then they would just run the Shannon's protocol, condition on y. But turns out that even if she doesn't, there is a way to do it, which only uses Bob's side information. So that makes this quantity really information theoretic, which means that what matters is just the information that Bob gains in the protocol, condition on what he has. It doesn't matter what Alice's knowledge was. So anyway, so the idea of this protocol is particularly interesting. And the way it goes is as follows. I'll do it for just this problem where there is just one sample from the source. This is also known as one-shot setting, if you guys have heard of it, and it's very useful, like even in cryptography and stuff. I'll go to that later. So the idea is that Alice applies a random permutation on X, which means that it's not a permutation in the sense of exchanging qubits. It's actually it takes the whole space of the random variable X into itself in some way. So x equal to 3 might go to x equal to 6 and so on. It's a permutation. Alice applies this thing on X. So X is a random variable on log X bits. There are these many bits. She does this permutation and she sends first few bits to Bob, basically. And here, it turns out the way Alice chooses this permutation is via some shared randomness. So Bob also knows what permutation Alice applied. So they have this information. She does this and then she sends this thing to Bob. It turns out that, so this protocol would fail if given a y, Bob didn't know, Bob had still some confusion about some x and x prime, which means that Alice sends these first few bits to Bob, remaining few bits still had some collision. So it might be possible that after this permutation, pi of x and pi of x prime agree on these remaining bits that Alice has, given Bob's information y. But turns out this happens with very small probability if pi is random enough. And then after Bob gets these bits from Alice, he knows which x must have been because there's no other x which would collide with it. And then you can finish the task. So is everyone fine with this at this point, or I could elaborate a bit? Yeah. It's a protocol. I mean, there might be some other ways, and there are other ways to do that as well. But it's a particular way in which Slepian and Wolf did this problem. But does that answer your question? Okay. So in fact, there are new ways to do that as well, and I won't go into them. But yeah, that I guess more explicit. But anyway, so notice that Bob is really using his side information y to do this thing. Alice is just applying a random permutation. So her operation doesn't depend on y clearly. That's sort of universal. Anyway, this idea is pretty powerful of random function because it was, well, if you've heard of this task, randomness extractors, it is used there very, very commonly. So what is the task of randomness extractor? I'll phrase it in a way that is more friendly for quantum versions later. So the task could be that, okay, you're given a joint random variable x and e. There's some distribution over it, and you want to apply a function on x in a manner that the output is uniform and independent of e. So a remark is that usually some additional randomness is required for this task to be efficient. Otherwise, you can prove that there exists some ways to do it. But if you're concerned about applying the randomness extractor efficiently in low-dip circuit, then you may have to have some additional randomness to do this thing. Anyway, so the construction by Trevisan achieves really small randomness. There might be other works, but it's not relevant for this talk, so I won't go into the details. Here's a very simple way to achieve a randomness extraction. Just apply a random permutation the same way as was done in the case of Slepian and Wolf. and discard all but these many bits. I think I skipped something, which was that H min is known as min entropy, and earlier there was H max. It is max conditional max entropy. These serve roughly the same purpose as the conditional entropy over here, but there are one-shot versions. I mean, they kind of their definition depends on the task and stuff, so they are more useful in some setting and otherwise. They all look like conditional entropy in the asymptotic and ideal setting. So, I mean, we could go into the details of the definition as well, but it's like you could, whenever you see this H and something on below, or I mutual information something below, just think of it as mutual information and so on. That's enough for the discussion at least. So what happens is that Alice discards pretty much everything except the first few bits, and turns out that these bits are uniform. Now, because a random permutation is a lot of possible functions like which you can apply. So what you can do is that you can simplify the construction much more and apply pairwise independent permutations, which means that they look random on two inputs, basically. So what you do is that you pick, a very simple way to do it is as follows. You pick two A and B from the same set X and assume there is a bit of group structure on X and so on, and apply this function, which is AX plus B, where you assume that multiplication is defined on the set X and so on, and do modulo X. Assume that X is a prime. So there are a bit technicalities, but the point is that it's a pretty simple function that you can apply on your random variable. You can discard everything except these many bits, and you will end up getting uniform on what you are left with. So, and it's just a linear, it's multiplication by A and X, which can be done pretty efficiently, and then addition mod some numbers. So these are all efficient operations that you can do. The constructions get even more efficient, but I mean, I'll have to skip that, but then you can look at this work, for example, for those things. All right. So any questions about the classical tasks that we discussed? Is everyone pretty comfortable with that? Yes. All right. Okay. So now let's just slowly go through the quantum versions of all these three tasks that we saw. So, okay, what do we have? So first, I'll kind of go in a reverse order. I'll first discuss decoupling. You guys might have heard of it. It's pretty. Anyway, yeah, this seems to. Oh, the battery's gone.
Oh, okay.
That's all right. Do you have one more? Wow, thanks. Oh, sorry. Oh, cool. This one. Oh, this one. This one. All right. All right. Sorry. So, what are the quantum versions of this task? They're pretty natural. They go in this very similar way. So let's do quantum version of randomness extractor. So what would that be? You're given a quantum state psi RA. I'm changing some names of the registers here. Earlier it was XE, and now I'm calling it RA. That's for consistency with literature if some of you are interested in looking at what is known. So you're given a quantum state psi RA. In this talk, R will usually be a system which is not in your command, in your control. And it would be acting the same way as the random variable E was acting for randomness extractor. So it's like adversary kind of thing, roughly. Depends on the task, but for this for the randomness extractor, R would be the adversary. So you're given a quantum state psi RA. Your task is to apply some operation on A. In fact, you can allow some additional ancillas and so on. And this thing should output, let's say, A1 and A2. We want R to be independent of A1 after we throw away A2, basically. So now the thing is that in the case of randomness extractor, what was left behind, which was A1, which is the same as X earlier, it was uniform. But in the case of decoupling, it depends on the scenario, whether you want it to be uniform or not. So this is just to keep in mind for later purpose, but you can ignore this thing for now. So there are very simple questions you can ask. Okay, what is the minimum size of A2 that I have to throw away to achieve this task? How can I make it efficient? Is there an efficient way to implement this task? So okay, so this is similar to what I discussed for randomness extractor. Now let me go to Shannon's task for a moment, and then I'll kind of try to connect this guy and decoupling later. So what would be the quantum version of Shannon's task? It was done by Schumacher in 1995, and what it does is that the source gets replaced by this reference who's sending something to Alice. In the case of Shannon's task, you could view a reference as establishing a correlation with Alice, and Alice is transferring this correlation to Bob. There's a viewpoint, you can take that, and you can do the same thing with the quantum case. It's more helpful because things are quantum and stuff. A reference cannot really take an X and copy it and so on, so you have to be more careful. But anyway, so there is a pure state shared between reference and Alice, and the task is that A has to go to Bob. This is simply state transfer. I saw a poster outside about state transfer, it may not be the same thing, but anyway. And then you have the version of Sliban and Wolf, which is state merging. So what does that do? There is a pure state RAB. B is with Bob, it's side information with Bob. A is with Alice, there's a reference. So in the classical case, R was XY, Alice A had X, B had Y, and just send A across. Simple. So it turns out that in the quantum case, these tasks are really connected to decoupling. And why is that? Let me just show you why quantum state transfer. Like it's essentially equivalent to decoupling. So let's see why. So what would Alice do in a task? Should apply some operation on A, get A1 and A2 for example. She would send A2 to Bob. Decoupling asks that R and A1 be independent. If that happens, then Bob can, by Ullmann's theorem, if you're aware of it, otherwise, like, if two states are product, then their purifications can be made product as well. So Ullmann's theorem would be the approximate version of that, and it allows you to Bob to purify reference separately and A1 separately. So as you can see, you have achieved the task of quantum state transfer if you have a decoupling. On the other hand, any protocol that does quantum state transfer makes R independent of Alice anyway because of essentially monogamy of entanglement, because R cannot be entangled with Alice if it's purified at Bob. So reference and Alice are going to get decoupled in any protocol that does state transfer. So they are same task. Same applies for quantum state merging. So does it make sense? Like, yeah. So yeah, sorry, I think I didn't. Yeah, I think I didn't describe the model here. So we allow quantum communication. If you want classical communication, totally fine. I mean, you can use pre-shared entanglement between Alice and Bob. I mean, you're allowed to. So Alice and Bob can start with some entanglement which is not already shared with reference. So yeah, so you want to minimize the communication. I mean, you could send the system A to Bob, but then it will not be compression, right? Because you want to send as less as possible. For instance, if A is already independent of reference, then you won't send anything. You will just let Bob just create A yourself. So you want to compress, like you want to communicate as less as possible. Teleportation, the standard Bennett et al., their teleportation would not work simply because that amounts to sending the whole thing to Bob. And decoupling and these kind of techniques are more clever way of doing the same thing. I mean, same applies to Shannon's theory. I mean, Alice could send X to Bob as well, like classical teleportation, whatever. I mean, whatever that is. But that's not compression, so you want to do something as less as possible. Anyway, so sorry, if that was not clear. All right, so what I wanted to mention here is that all these three tasks, like decoupling and these things, are very well connected. And in the quantum case, it's even more clear that there's a connection. I mean, in classical case, Alice doesn't have to make herself independent of the source to send the X to Bob. But quantum case, it's going to become necessary. So anyway, so far, I hope you all understood it. So far, I just discussed three basic classical and quantum information primitives. Any questions about this? Right. Yeah. So it's use of decouplings, I guess. Motivation. I mean, I would say these were the motivations in some sense. Right. But yeah. But okay. Right. Okay. So seems like decoupling is a very powerful technique. So let's see where it has been used so far. Basically, almost all quantum communication paradigms. Quantum state merging, what I mentioned earlier. Quantum state redistribution, somewhere in channel coding and things like that. I won't discuss any of this, so don't worry about that. Yeah. So no, I'll discuss those things basically. So A2 is what Alice is communicating, and that's the motivation to keep A2 minimum because you want to send A2. So it's a resource. You want to keep it as less as possible. Similar to randomness extractor, right? What you want to discard is as less as possible, and then get as much uniform bits as possible. So it's like similar things. So anyway, uh, like I mentioned, randomness extractor can also be viewed as a decoupling and so on, and you can do it with, when E is a quantum system, then you can do it, and there are several results in that direction. It's not exhaustive at all, it's just first two results. It's also useful in quantum thermodynamics, in this very nice paper, you can check it out. It's also very important for black hole physics, apparently, and decoupling allows black hole to be independent of quantum information which comes out and so on. But okay, I won't discuss this. Anyway, so this seems to be a very useful primitive. So what are known decouplers? Just like a random function was doing very well for the classical task of slip and wolf, if you notice, a random function would also work for Shannon's protocol, roughly, but a random unitary works in a similar way for quantum case. Basically, you apply a random unitary on your, it's like random permutation is a classical unitary and so on, and it's like random unitary is a quantum unitary, random quantum unitary. So this achieves decoupling after you discard some system. As I mentioned earlier, that random permutations can be replaced by these simple functions, ax plus b, because these are much easier to deal with and so on. And in the quantum case, so far it's known that the quantum analog of that thing is known as a unitary 2 design, which basically achieves what would a pairwise independent function would do. It has the same effect on quantum states. Now, what are the constructions of unitary 2 designs? So these authors give really nice construction actually. So if you want to do decoupling on n qubits, so you need a circuit of only nlogn size, log and depth, where n is the number of qubits. N is not even the dimension, it's exponentially small. And there are some additional ancillas required in the task. So it was a construction from 2016. Another very nice construction by Winton Braun and Omar Fawzi. They gave a decoupling method using a random quantum circuit in which every gate was chosen in using some physical process by some random physical process. So these are the two constructions that I am aware of which are pretty short, which are pretty efficient so far. And then there's this method of convex-split that I'll talk a bit more in details later. It does decoupling as well. It's very different from these things that I'll talk about a bit more. It's not very efficient so far. Okay, and maybe the unitary inside the black hole also does decoupling, but don't take my word on it. I have no idea. I just heard this from Perimeter Institute people. They said black hole is a decoupler and so on. But anyway, so okay, so now what is this talk about really? This talk is going to be about this particular method and trying to find schemes that are better than these methods. I will discuss soon reasons to, so in this talk there are two components in this talk. Sorry, I'm saying it right now. I should have said it way earlier. And the purpose of both these components was to make this method more efficient. If you don't care about this method, you can view them independently, and they might be of some interest. So okay, now I'm going to go into the results slowly. Let's look again at this quantum decoupler and randomized extractor. These two tasks. So as I discussed earlier, randomized extraction can be done with pairwise independent permutations, which is just ax plus b, this very simple function. Quantum decoupling turns out to be a bit more complex than that. You apply these unitary 2 designs. Usually these are random Clifford gates and so on, or in the constructions I discussed earlier, they are a bit more complex versions of that. But they're shorter, but they definitely use some very non-trivial gates. So you could just ask this question, just out of curiosity, that what happens if I apply a randomness extractor function on a quantum state? Would that do decoupling or not? For example, could I apply a random permutation and see if decoupling happens? So this was studied in this work in 2011. And the author found that if there is an entanglement in some sense, like if the conditional mean entropy is negative, then random permutations don't seem to do decoupling, which sort of makes sense, right? Because I mean, these random permutations are classical operations. They should only do classical decoupling. They should not be able to do quantum decoupling. Like if there's an entanglement and so on, they should not really work out. So it really feels that you need these techniques. That, for example, you need two designs or this kind of really quantum techniques to achieve this task. The result in this talk is that you can do quantum decoupling by just addition and multiplication modulo prime, which means that it's a purely classical circuit, it's efficient, and it's just 2 times more hard work than what would you do for doing classical randomness extraction, nothing more than that. There are some new perspectives here as well, which I'll talk about soon. But anyway, so this will be the one of the part of the talk. The second part will come later, just the second theorem. It's very informal, by the way. So before I go into what this decoupling looks like, I'll for a moment pause on this picture. So this is a lemma which is a way to do decoupling. There are several uses, but what it does is as follows. It randomly prepares the following state. So what it does is that it chooses a very large n, and so let me just remind you, R was the resistor, and this should have been A actually, sorry. I renamed it to B. And this is the quantum state RA that we wanted to decouple in some sense. It's sitting over here. I will add lots and lots of ancillas. The state here could be the same as the state here. It doesn't have to be the same. It can also be different, but anyway. And what I do is that I do the following process. Randomly, if I choose a number from 1 to n at random, uniformly, and if I get 1, then I just don't do anything to the state. If I get 2, then I do a cyclic permutation by 1, like just 1 cycle. If I get 3, then I do it like 2 cycles, and if I get n, then, so effectively what I'm doing is that I'm taking this correlation to here or here at random. I do this thing, and I throw away my choice of randomness. This is the state I get in the end. It's a convex combination of these states. And it turns out that this, if n is chosen large enough, like roughly the mutual information between these two resistors, which is like, if n is chosen enough to capture the correlation between these two resistors, then it turns out that it becomes independent. So this is a process to do decoupling, as you can see. Now, for several applications, you can also do the reverse direction. If you have a state of this form, you can view it like this, just like anti-decoupling in some way, I don't know, and you can do protocols out of it. So, so I guess, is everyone comfortable with this particular statement? Like, you can view which way you like. So you could start here or start here. Or from the left. Also, the assumption would be that you have a system R, and these B1, B2 are all IID. They're the same quantum states, independent. And if there are enough of them, then it looks like a mixture of these guys, where all the red dots are the same quantum state. All the blue connections are this psi RB, and R is the green guy on the top. Right. So no, then yeah, I agree. So the decoupling which kind of only acts on the state, on the resistor that you have, that would not work. But then you can use additional randomness or additional resistors. And then notice that I agree. I mean, so in the sense that if you wanted to do a decoupling by just acting on the resistor that you are interested in, then you would not be able to have these other resistors. But you can take a different viewpoint, which basically says that, okay, you can add additional resistors and return them back. It's like it's more of a catalytic framework. It's like, you add these resistors, do this random swap, random cycle, and then as a result, R is independent of everything here. So R and B1 are decoupled. At the same time, everything else has been returned to you. So for example, even in the case of randomness extractor, if I'm choosing a random function, I would add some additional randomness and choose my random function. It's just that the randomness is very small in the randomness extractor, but it's just that in this case, I'm asking for a lot of additional states. Basically. Does that answer the question? Actually, it's n here. It's a lot. It's huge. It's like exponential in the number of bits. Like approximately the number of, yeah, approximately the size of this register. So it's too much. I mean, I agree. But I guess for communication perspective, if you don't care about the resources like entanglement and so on, then this is like pretty optimal way to do it. So this is a way to decouple, and basically that's the question that we were worried about. That okay, this result uses too much additional resources. So what can I do about that, basically? So let me just quickly mention some properties of this method. Oops, sorry again. Okay. Okay, that's all right. Okay. So this method over here is a quantum version of what is known as rejection sampling based protocols in communication complexity. It's been very useful for proving communication complexity results, and it's like the direct quantum version of that. It can really be used to construct protocols for various information theoretic tasks, and for example, channel coding, source compression, randomness extractor, you could do all of them with this, but I mean, in comparison, the previous techniques kind of didn't quite do everything at once and so on. It's like a more direct way to do this task, and I mean, I could give you several direct ways to do it, but then it's useless if you don't get something better than previous work. So one can achieve near optimal communication in many scenarios which are not known earlier, and you usually always get smaller communication than what is known earlier. So this is just remark you can zone out in this part, and it also found some uses in like out of beyond decoupling. So I mean, I like to think of it as something that implies decoupling kind of method, but it's not really the same. So anyway, now let's see how does that method, this convex-split method, compare with the decoupling via random unitary. So if you notice that decoupling via random unitary gives you an output register which is pretty uniform in what is left in the register that is left behind. Turns out that okay, this is okay for the task of, let's say, randomness extractor and so on, but it's too much work if you just want R and A to be independent. For example, if R and A were just independent and A is not uniform, then random unitary protocols would still do some hard work and try to make A uniform by discarding some part, basically. So that would be unnecessary hard work. So these authors kind of found a way to get around that earlier, but I'll talk about this later, but then I'll also talk why there were some issues with this. This convex-split method, the nice thing is that it avoids this extra hard work. So if R and A is already independent, in this picture, if R and A is independent, then you don't have to do anything. Choose n equal to 1. Nothing else is required, basically. So it turns out that this technique directly gives you good communication wherever you want, but the issue is that it requires too much entanglement. As you saw, there were lots and lots of red dots in that picture. Whereas this decoupling via random unitary requires very less entanglement. So, so this was another motivation for us to consider this work, and I mean, it's up to you if you care about this or not. Because I mean, essentially the point of this, one half of this talk is going to be about fixing this problem with this convex-split method, and basically, can we really get best of the both? Like, can we have a method in which I do little bit of work, just enough to let the decoupling happen, and still require very less entanglement for the task? And the answer is yes. So that's what we'll see. We require as of the same order as used in decoupling by random unitary. All right. Now, I'm going to answer the first question now, which is basically how do you do decoupling or so on with very simple classical operations. Before that, any questions so far? Anything you would like to be clarified? No? Okay. All right. So what do we mean by a classical unitary? And it has to be defined properly. So I call unitary classical if for a choice of your basis vectors, let's say you choose computational basis, like 0, 1, and so on. It only takes basis vectors to basis vectors. It doesn't mix them up. Like it doesn't create coherence there. So if you think about it, in this convex-split method, I was just swapping registers up around. That's a totally classical operation, because if I act on computational basis, it will stay in the computational basis. Because 1, 2, 3 will go to 2, 3, 1. That's still a classical operation. Unfortunately, the number of registers are so many that it's not efficient at all. By efficient, I mean efficient in the number of bits. To send this B1 to Bn would require me lots and lots of swaps, which is huge. So what we found is a collection of unitaries which behave very much as this cyclic operation in the convex split, but they only require 2 registers. That's it. And what's interesting is that the way we found these unitaries kind of uses this pairwise independent construction of functions, but in a quantum friendly way. So I'll go ahead and describe the unitary, and I will not give the proof. So what we'll do is the following. So like it kind of goes back to what Shaudi was pointing out. It will still not act only on the A register. It will require 2 more additional registers, but you will return back everything except a small part that is discarded. So what I'll do is that I'll introduce registers A2 and J, where A2 is just like the register A you want to decouple, and J is something that will be very small and it will be discarded. So what I'll do is the following. J will act as a control. Just like in the convex split, they just choose a randomness to swap. J is a control. Condition on J, you look at I on A and I prime on A2. What you do is that you do this following simple linear operation on these two, which basically amounts to taking I and adding this function basically, I plus I prime minus I j mod A and so on. So this is very similar to what happens in the case of random, like this pairwise independent permutation basically. And you do that and you throw away J. And once you do that, it turns out that everything becomes independent. Like A becomes independent of R and A2 stays independent of R and J goes away. So all the correlation of R gets transferred in J and it escapes. The point is that how is it different from, so for example, another point is that you could just use the same operation to also do randomness extraction. Because it's a classical operation, it's efficient, the same way as linear functions in the randomness extractor are. So you could just, with just additional extra register here, you could do the randomness extractor. Another key point is that in the case of randomness extractor that I discussed earlier, this AX plus B kind of construction, one was conditioning on A and B. One would introduce A and B as additional randomness. Condition on them, one would do something to the register one wants to decouple. In this case, I'm changing the randomness that I introduced and then discarding that away. So that seems to be creating a difference because that seems to be also working out for the quantum case. And I don't need unitary 2 designs and so on to do the same task.
One question.
Yeah.
So could we think when we do this operation we just for J, is that the same thing as doing like a stochastic quantum operation?
Yeah. So it turns out that in the decoupling picture, like throwing away a quantum resistor and throwing away classical noise are similar because I mean it's a bit of a nice argument which kind of uses super dense coding and teleportation kind of point of view. But anyway, so you could just think about discarding something. So we discard something and then everything else becomes independent, basically. Sorry? So A2 is uniform and J is uniform when they started. Totally mixed. Yeah. And after that, A2 stays totally mixed, A becomes totally mixed, and J goes away. So, sorry? So J is going to be of the number such that the size of A2 minus size of A minus J is the mean entropy. So what you gain is mean entropy, basically. So in the sense that initially A was not uniform. I added J. So notice that A2 doesn't change, it stays the same. So amount of randomness I'm gaining in the process is just the difference between A and J. And that has to be mean entropy. So basically J is like log of A minus the mean entropy. Yeah, so dimension of A has to be prime. So we kind of course, yeah, we do that. Oh, sorry, yeah. No. This function is 2-wise independent, still 2-wise independent. This is just, this function is applied here. This joint operation has the same algebra, roughly, as this cyclic operation of convex split. Like if you multiply them together, if you notice, if I take J and J prime and compose them together, then J and J prime get added. So it kind of goes the same way as this swap or cyclic shifts we're going. Yeah, so it kind of does. Still, yeah. So I mean, these functions are still pairwise roughly. I mean, the key point is that we kind of get away from that point of view now, because that's not necessary here anymore. I mean, even if it was not pairwise independent, it wouldn't affect the construction. That's the point, basically. Yeah, it's very simple. So what I'll do is that if A is not a prime, is 2 to the power 30 or something, some weird numbers, there's always a prime between a number and its twice. It's like Bertrand's postulate from 1800 or something. So I'll just add an additional qubit and view the whole system as I'll slightly expand the dimension, like implicitly. And things still stay linear. I mean, I agree, this technicality has been discussed in the paper more carefully, of course. Yeah. So one has to be careful about that, but that kind of, I mean, even in constructing pairwise independent random extractor, you would worry about these issues. If X was not prime, it was bits and so on, then what would I do and so on. But that works out. It's not too bad. So anyway, so that's fine. So this kind of answers the first thing, that can I have very efficient classical operations that do the decoupling. So that's fine. Now, this was one aspect, and now I'll move on to a totally independent aspect. These two together will be useful for reducing entanglement in the convex-split method. But the point is that if you just care about this aspect, then you can totally sleep out, just go to sleep, because this thing is now a slightly different problem, slightly different construction. It has some different task. So like I discussed earlier, that in fact here as well, what is left behind becomes uniform. So if A was already independent from R and still not uniform, then this method would still, just like decoupling by a random unitary, do some extra hard work and make A uniform as well. It's like a bit additional effort which you don't want to put, to be honest. For communication setting, this is good to put for cryptographic settings. For a communication setting, you would not really want to do that, because you don't care about uniformity, you just care about sending stuff around. So one thing that you can notice is that in the asymptotic and ID setting, when there are many copies of a state, because of this typicality argument, the registers of interest are always usually pretty uniform. I mean, so for example, if I take a random variable x and take zillions of copies of that, with high probability, most of the mass of the probability is in a uniform subspace, pretty much. That's why all these techniques, this like decoupling by random unitary, does very well. In fact, achieves optimal answers and this as well would achieve optimal answers in the asymptotic and ID setting, like when there are many copies of the state. But in the one-shot setting, the issue is that they can be profiled like this. That's why I drew it here. They could be profiled like this. It's not uniform, and then you don't want to make the hard work and so on. So this issue was already recognized by these authors who kind of wanted to get one shot near optimal quantum state merging. So if they did just decoupling, then they would face the same issue. If the state to be sent was already independent of R, then they would be doing the hard work. So how did they resolve it? So what they did is that they took this profile over here. I don't know if you guys can see it. Sorry. So you take this profile, and you divide the distribution into many parts, such that the number of divisions is log of the dimension. So for example, I could divide 1 and 1 minus epsilon and epsilon square and so on, like divide into many small chunks, so that within each chunk, the distribution is like all the probabilities are within a factor of 1 plus minus epsilon of each other. That's pretty uniform. The number of chunks I need is the log of the x. So the number of bits of the chunk, the number of bits required to describe this chunk is log x. So that's a bit small cost. So they did this trick, and they kind of, and then they ran decoupling protocol inside each chunk. So it was already uniform, so it was pretty optimal there, and then things worked out for them. So I mean, it's just said in word here. So divide the eigenvalues of the state you're interested in into many chunks or blocks. Run decoupling in superposition, because everything has to be done in a quantum superposition way, but then you can use embezzling states to do that. So you do that, and then with this additional cost of log A, things work out, and they could prove nice results like they could reprove reverse Shannon theorem and so on. quantum reverse Shannon theorem using these techniques and so on. So up to this log A factor, they had pretty good answer because they were able to do decoupling pretty well. I mean, they didn't put the extra effort that random unitary might have to apply. The issue is that this technique somehow, for reasons I don't understand, so please don't ask me, it doesn't work for other channel coding scenarios. This division of chunk, it works well for some information quantities. It doesn't work well for other information quantities. So this point was already there in some works, but if you don't care about it, we can move on. So issue is that we wanted a method which kind of works everywhere. It works where their method worked. It works also where their method didn't work. So for that purpose, we kind of did something different. And this takes an idea from computer science, which is known as correlated sampling. So what happens in the correlated sampling method is that you want to, Alice and Bob kind of want to output a random variable which is equal with high probability and so on. So a part of their construction is the following, which I have described here. Sorry, again. So here's a quantum state or random variable. It's like psi A, which is summation over A, PA. You want to make it uniform, and it seems to be crucial for the correlated sampling case, so I'll just describe it right here. So what you do is that you condition on A, you add some uniform randomness in a space of size proportional to 1 over probability of A. So what you do is that you look at A and choose this E that goes from 1 to some big number times P of A, and then that gets normalized. As a result, the P's get cancelled, and the whole state over here is uniform jointly in A and E. So this is a procedure which starts from A and it can create this guy. So it kind of realizes any random variable as a marginal of a uniform random variable in a larger space. So okay, so how do we use it? Yeah, so that's what's written over here. Psi is a marginal of a state uniform in support. So notice that the thing that I add depends on the A I'm interested in because you have to normalize the probability. So we also do it coherently using embezzlement and stuff. And what's nice about this technique is that it kind of does not change any information quantity that we're interested in. And it is able to kind of make things uniform. And then you just run any uniform protocol. So, okay, so that's about it pretty much. I did, I guess, before time. So what you do is that you take this method, you take the classical decoupling method, join them together, and that essentially gives you like a way to do this convex kind of technique using small entanglement. These two might also be of independent interest because you can use this in some scenarios you like, you can use the decoupling one in some scenarios you like. I mean, for us, it was the joint use that mattered, but I mean, it depends on applications, of course, which you want to use. So, okay, I will skip to conclusion now, quickly. So what we have here is a way to achieve near-optimal results in many communication problems using small entanglement as well, which was an issue in the earlier convex-split based methods. And we could exponentially improve the entanglement required in this task, and we could also do classical decoupling, sort of, like decoupling by classical methods and so on. And that's about it. Thanks. Right, so, well, for one thing, in communication complexity, you want to compress, like you want to send as less number of bits as possible. So, in general, any technique which you give, which allows you to compress or send less number of qubits to do a task, that can be useful for various communication, like for proving direct sums and so on. Like, if I can compress to the information content of the random variable, then I can do direct sum after that because information theoretic quantities have nice additive properties. So yeah, so whatever technique I mentioned, one can use them in communication knowledge. They're more useful in one-round protocols for now, but I mean, one challenge is to kind of do it for multiple rounds, and that goes to this problem, like how do you do quantum state redistribution using these techniques? And that's kind of undergoing work basically. So yeah, in quantum network, sorry, did you say quantum network? Did you mention quantum network? Right, so all these techniques here, you can just apply them to get protocols for quantum networks. Like broadcast channel, I want to send message to both you and you over there, or both of you want to send message to me, and so on. So you can kind of give protocols for all these tasks, which you can prove them to be pretty optimal in some cases. Communication. Yeah, yeah. And now the point of this, the whole talk was basically to also try to get optimality up to constants in entanglement. So our entanglement still suffers a big like it's optimal up to some big constant, but that's still pretty fine. It's much better than having exponentially large entanglement. That's too much. But yeah, so you could plug these things and get protocols for all these network scenarios and so on. In the channel theory sense. Okay. Mm-hmm. Mm-hmm. I see. Right. So for example, if you want to share EPR pairs, then it says that you don't start with any EPR pair clearly. So there are entanglement unassisted versions of this as well, but I would have to look into specific details to see if that can be applied or not. There are also previous, so for example, Holevo's protocol kind of could be generalized, and that could give entanglement unassisted network protocols. But you could use that, for example, instead of these. So in this case, difference comes really when you have entanglement assistance. If you didn't have entanglement assistance, then previous techniques also were doing pretty well, basically. So you kind of, I guess one has to precisely look at the question and then try to see if it's useful or not.
So in general, when you have a description of a channel, how easy or hard is it to compete these one-shot?
Right. So if you don't care about some additive constants in your loss, then it's usually as hard as, as far as I know, as computing assimilating an IID capacity, because you can always rephrase these one-shot quantities in terms of Renyi entropies, and so you can show that Renyi entropy is achievable, and it's just a matter of asking, is a Renyi entropy harder to calculate than relative entropy? So then you can do that. So the only difference can come between these, like computing Renyi entropy and relative entropy.
So computing in the ID case, that's something like maximizing over time as much as space.
So for the entanglement assisted case, indeed, yeah. So maximizing over, there's a single letter formula which you can use, and yeah, right, yeah. But that's a different branch of that's not really a protocol construction. That's rather just analyzing the communication and then seeing whether you can